And new devlog. Quick reminder, the portfolio is already live and you can test it on brunosimon.com. All I'm doing now is finishing the devlog series, and we're getting close to the end. This episode is about a topic that was really stressing me out: performance. The more feature I was adding to the portfolio, the lower the frame rate. At this stage, I was usually working on a full HD resolution, pixel ratio of 1, high frequency screen on my MacBook Pro M2. And the frame rate wasn't looking good, running between 70 and 80 frames per second on the landing. You might think that 70 FPS isn't that bad, but it's quite a small resolution with a decent device. As I often say, the web is a place where things are easily accessible, and it should stay that way. Not an easy task when building 3D applications. And I think that a bad frame rate really spoils the experience. Not gonna lie, this matter kept me up at night. So I used all the tricks I could think of, and I'm going to explain everything. Note that even though I was focusing mainly on performance, the goal was also to reduce the weight as much as possible. In a recent three.js update, they added the inspector. It's a cool debug UI that we can toggle with this little button. It shows some performance-related stuff, info about the experience, some renders like the shadow map, and it can be used as a debug UI, which I didn't use since I already had TwigPane, but the rest was welcomed and helped me monitor the performance. When you draw a mesh on screen, sending the instructions to the GPU takes a little bit of time and memory. If you do it for 1,000 meshes, you're going to have performance issues. But if those 1,000 meshes are using the same geometry and the same material, you can draw them all at once thanks to the instance mesh. And by the way, even though I didn't need it, you can also do the same trick with a set of geometries sharing the same material thanks to the batched mesh. I was already using the instance mesh here and there, but there were more elements that could use it, like the explosive crate, benches, fences, bowling pins, lanterns, etc. Do you ever think you had a genius idea and then realize it's a well-known technique? Well, it happened to me with the palette. I wanted to reduce the draw calls as much as possible for meshes that stick together. Let's take the bench as an example. As you can see, there are two materials, wood and metal, meaning two meshes, resulting in two draw calls, right? First, don't even try to merge them in Blender. They will look like it's the same geometry, but the GLTF exporter will export two different meshes. One option is to use the vertex color. We merge the geometries, we use only one material, we set its output to the vertex color, and we paint the vertices. And that's actually a good solution. But the two main issues, other than having to find tricks to paint the vertices without doing it manually, is that 1. The buffer gets heavier since we have one color per vertex. It's not that bad, especially since it's low poly models. 2. If we want to change a color, we have to vertex paint it in every object. So, what is this palette alternative I'm talking about? I created a very small texture, painted every color I have in the scene as one pixel in that texture. and use that texture according to the UV to pick the color. The main benefits are that 1. The UV can be compressed a lot. 2. It's easier to tweak the colors. Using this technique, I went from 2 draw calls for the bench to only 1 draw call. Not a big deal, you might think, but I also went from 5 draw calls for the kiosk to only 1 draw call. And almost everything in the scene benefited from this improvement. Before the update, I was running at 375 draw calls on the landing, which is a lot. And after the update, I was running at 222 draw calls only, which improved the frame rate a lot. By the way, those draw calls include the shadow map too. And that was a huge relief. But it wasn't over yet. When checking the network tab, I noticed that many of the UI images were being loaded because they were in the DOM, even though the container had display none. This is the default behavior with HTML, but it was a waste of bandwidth since those images can't be seen before the experience starts. The solution was quite easy. I added loading equal lazy to all HTML images. And with this, the image will only load when actually visible in the DOM. For the water, I've been using the hash blur, which looks crispy. And I love it, but in my quest for better performance, I knew I had to do something about it. Even though the hash blur isn't actually that bad for performance, there are more performance solutions, like the classic box blur that I already used to create the depth of field effect. It doesn't look good if too wide, but it's cheap and does the trick. The terrain texture had a 1024 by 1024 resolution, which isn't too bad, but I knew I could do better. So I resized it down to 512 by 512, which is 4 times less pixels to load and a much lower memory footprint. I also changed the floor geometry resolution and I went from 1 unit divisions to 1.5 units division for both the visual mesh and the physics height field, without having much of a visual difference. Many of the areas were doing stuff on each frame, like the bowling pins testing if they are down, the career stones updating according to the player position, or the behind-the-scene portal shader also updating according to the player position. Even though three.js frustum culling prevents meshes outside of the frustum to be rendered, this process of testing what is inside or outside the frustum is heavy, especially with a complex scene like my world. So I implemented a simplified culling only for the areas. The goal was to completely deactivate an area when it's outside of the view, preventing it or its children to be rendered, but also preventing any useless update. I could have used the three.js frustum culling for the whole area, but since the world is almost flat, I'm talking about my portfolio obviously, I decided to implement my own cheaper solution. In Blender, for each area, I created an empty circle corresponding to the bounding. In three.js, I calculated a quad going through every corner of the view against the floor. On each frame, I did a little bit of messy math to test if the area bounding was inside the quad or not, toggling the area accordingly. And there you go. Only areas in the view were being updated and rendered. With the world getting bigger, I was having more and more dynamic objects scattered everywhere. RayCursor, the physics engine I'm using, already have built-in default optimizations, like putting a body to sleep when it's barely moving. But after doing some tests, I noticed that many objects stayed awake even though they were outside of the view. Here's a good example with the cookies. Look at them piling up. And rolling. Come on, get to sleep. So, what I did was to put any object outside of the view to sleep. First, I rounded the view focus position and only tested objects if that rounded position changed, just to avoid doing too many updates. In the part where I was going through every object and updating the visual version to match the physical version, I tested if the object was outside of the view and put it to sleep if it was the case. This can lead to weird behaviors, like objects stuck in the air if we go really fast, but the amount of active objects went down so much. Huge win for the CPU. Another classic optimization is about sorting. three.js already handles sorting in order to avoid overdrawing. Overdrawing happens when you draw a mesh in the back and then another mesh in front of it. When doing so, you draw those pixels twice, even though we can only see the closest fragment at the end. The fix is simple. Draw the close one first, then the back one. And thanks to the depth buffer, those fragments won't be drawn twice because the GPU knows there is already something occluding that fragment. Which is why sorting is important. But sorting is being done on each frame and can be a hassle for the CPU, especially with a complex scene like it's the case here. Solution 1. Do the sorting yourself. This solution only works if you have a more optimized way to do the sorting. And there are plenty of algorithms that can help, although it depends on the exact scene and how objects are being dispatched and animated. But after a few attempts, I didn't get a better result. I'm quite sure I did something wrong there, but couldn't figure it out. So I went for the solution 2. I deactivated the sorting. When you don't have that many meshes in front of each other, it's actually quite a good solution. In a way, you move the hassle from the CPU, because less sorting, to the GPU, because more overdrawing. I reviewed every shader, removed every overkilled features, and optimized them as best as I could. As an example, the wind shader was made so that the lines always face the camera, kind of billboarding but for lines. But since the camera angle never changes, I could just rotate the geometry faces. Or the road with the little details made with the hash texture. Those details were animated according to the camera position, like for the snow. But we couldn't really see it unless the camera was really close, so it's gone. Remember the RayCursor? It's a class I made to handle cursor interactions. It was already well optimized since I was only updating it when the cursor moves, but also because I was using custom intersection systems, mostly relying on spheres, which is a lot more performant than recasting a triangle-based geometry. But I completely forgot to filter active intersects only. My mistake. Until now, I was relying on Blender to Draco compress the models. To have more control over which file is being compressed and how exactly, I created a Node.js script going through every GLB file in the static folder and compressing it. I used the gltf transform library, and it's amazing to see the amount of tweaks we can apply to the models. And that's where I discovered that the palette technique already exists. Well, good thing, because I didn't know how to call this trick, and palette sounds like a pretty good name. Since I was doing most of the geometry-related optimization directly in Blender, handling the palette by myself, and had a very specific hierarchy, in the end, the main benefit came from using the quantize only, which reduces the precision of the many numbers, making files smaller and faster to load. The trick was to find the lowest value without getting this kind of result. For the textures, the first thing to understand is that PNG is really not suited for 3D experiences, especially for the web. I was using PNGs until now because it's a lossless compression, so that I can work with good quality, and it's also easier to manage since it works with most 2D softwares. But the files are heavy, and the memory footprint is much bigger than a GPU-friendly format. Speaking of GPU-friendly formats, the two main solutions are ETC1S and UASTC. To sum it up, use ETC1S when you want very small files at the price of quality, and use UASTC when you want high-fidelity files, although not perfect, at the price of a heavier file. In both cases, the memory usage is much smaller compared to a PNG, and the buffering is also faster. Also note that you can build and embed the mipmap version directly in the file at the compression stage. First, I added the ETC1S compression to the gltf transform previously mentioned, so that the texture embedded in the models are well compressed too. Then I took care of every PNG textures I had in the static folder, like I did for the models. I used the 2KTX library, but this time I wanted more granular control. So I used regular expressions on the file path to apply very specific compression parameters. As an example, for the terrain texture, I use UASTC to preserve the quality, generated mipmaps, linear encoding, and only RG and B channels, no need for the alpha. On the other hand, for the slabs textures, I use ETC1S to highly compress it, linear encoding again, but only the red channel since it's a grayscale texture. Both the models and texture compression ended up reducing the portfolio size a lot, but also sped up the buffering and considerably reduced the memory usage. Same deal for the UI images we see in the modals. I used WebP instead of PNG and did the compression in the same Node.js script, using the Sharp library. After going live, three.js got a nice update with a new sampling for the PCF shadow map. The idea is that to get a smoother drop shadow, the shadow map is being sampled multiple times with a little bit of variation between each sample. And this new version uses the Vogel disk to sample the shadow map, which results in this smoother but at the same time crispy shadow. Even better, it's more performant, although it depends on the exact setting you choose. I just love the result. Doing all these optimizations helped so much and the experience was working smoothly. But some old mobiles were still struggling, especially on iOS. Apple recently added WebGPU support to iOS devices, which we've been waiting for so long. Unfortunately, iOS users are not updating their devices fast enough. And as I'm recording this video, many iOS users won't be able to see the WebGPU version. Fortunately, the WebGL backend automatically kicks in, saving the day, but performance isn't as good. And in general, mobiles aren't as powerful as our computers, so I needed to do something about it. These days, there are ways to test the device capabilities, but they are not accurate, the score is not always relevant, and some constructors obfuscate hardware info, preventing those solutions to work properly. Even monitoring the performance directly during the experience and trying to adapt it isn't safe and relevant. So I went for a simpler solution. Using a regular expression, I tested if it was a mobile, and if it's the case, I switched to a low quality setting. Here's what changes in low quality: smaller shadow map, cheaper bloom pass, closer camera, yeah I know, that's a silly one, no depth of field, and no water blur. And that's all. Not much of a visual difference, but significantly improved performance. And the user can still change the quality between low and high whenever he wants. Having good performance was such a relief. I felt like nothing could stop me now, and that I was really close to the end. But it was like it was missing something really important. Ah yeah, sound design. But that's for the next devlog. If you enjoyed the video, please subscribe and leave a like. Follow me on X or Blue Sky for more creative and coding stuff. Don't forget that the portfolio is already live on brunosimon.com. And if you notice performance issues, please tell me in the comments. And I will see you in the next devlog.